So thus far we have seen how to do volumes and areas of curves, but what about the length of a curve itself? And to do this, we will also have to rely on integrals. And so in order to derive how the length of a curve can be found, let's actually look at a curve. So let's say we're interested in finding the length of sine x, for example. So we know that this is how sine x looks like. And let's just say that let's try to represent this as a Riemann sum, and then that will help us derive what the integral will look like. So let's say we wanted to find the length from some interval xk minus 1 to xk. So this is like a small interval. And if you want to find the length of the curve between those 2 points, a good approximation would be to take this length, this horizontal length, call it delta xk, and then this vertical length, we'll call that delta yk, and then we can just approximate the distance as a straight line distance between them. And actually, let me switch the color so it's more readable. So we can estimate the distance of the curve as a straight line distance, and that estimate will just be the square root of delta xk squared plus delta yk squared. So you can imagine that as we reduce this length of this interval towards zero, so as this horizontal length gets towards zero, this square root term that estimates the straight line distance gets closer and closer to the actual distance of the curve, right? So in our Riemann sum representation, we're basically summing up all the intervals. So the sum of all the intervals of square root of xk squared plus yk squared. And this doesn't help us in the form that it is in right now, because to form an integral out of this, we need the Riemann sum form. And remember, recall in the Riemann sum form, we had some function f of ck times delta x or delta y, depending on what variable we want to take our integral with respect to. So motivating the fact that we need a delta xk, we can multiply by xk on both sides, and then these are all deltas over here, so we multiply by delta xk over delta xk, and that's just the same thing as multiplying by 1, so this is a completely legal move. But what this helps us do is we can rewrite this sum as such: delta xk squared plus delta yk squared divided by, and this is all under the square root, delta xk squared, and then this other numerator delta xk can be over here as well. And then simplifying further, we can get square root of 1 plus delta yk squared divided by delta xk squared times delta xk. And now this is starting to look much more like a Riemann sum, right? We have some function over here, which can be f of ck, and then this is just that delta x that we needed, and we're summing up all of those. And we know that now to represent this like further as some point on this graph, we know that through the mean value theorem, there must be a point on the graph that represents delta, because so delta yk divided by delta xk, all of that squared, just represents the average rate of change in the interval, in the kth interval. And we know through the mean value theorem there must exist a point where the derivative of our function that we're looking at that point equals the average rate of change. So the mean value theorem allows us to write this sum as 1 plus dy dy over dx of some evaluated at some point c. All right, and then all of that is squared times delta xk. So we're still in the realm of the Riemann sums, and we still have not gotten the integrals, but as we take the limit of our and we shift our norm of this delta x to go towards 0, then what happens is the sum becomes an integral like we have seen before, And essentially, we get that to find the arc length of like a curve on some interval between, let's just say, like A to B, right? These like interval, these average, so like this average rate of change becomes the derivative at the point. And what I mean is this sum gets transformed into just an integral of the square root of 1 plus dy over dx squared times dx, because we're now getting rid of this summation by taking the limit as our delta xk goes towards 0, and hence we're now just calculating the derivative at a specific point. So this integral, if we take it between points a and b, that gives us the length of a curve between a and b. But before we can just blindly use this formula, we have to see some of the assumptions we made in this derivation process to get to this final stage. One of the assumptions was that our first assumption was that we assumed that the derivative of f is defined on a through b, right? That means that in order to be able to find this arc length and to use this formula that we just derived over here, we must have that the derivative of the function on the interval a through b must be defined on all of those points. And this is often called the fact that a function has a continuous first derivative can also be called as a smooth function. So if a function is smooth, it means that the first derivative of that function is defined on that entire interval that we're worried about. So we must have a smooth function in order to be able to find the arc length through this formula that we just defined. And notice that in the key step was really over here where I pointed the arrow, where we or technically over here where I multiply by delta xk divided by delta xk, allowing us to rewrite it into a Riemann sum format. I could have very much just multiplied it by delta yk divided by delta yk. And what that would have done is that would have just given us another formula to find the area or to find the length of a curve, and it would have looked like this: 1 plus dx over dy whole squared times dy. So this is another valid formula to find the arc length of the curve, except now we're writing it in terms of the integral being with respect to y. And one thing to note that for a specific curve, this b and a, these limits, are not the same necessarily as the limits of the b and a for the same curve when we're doing it with respect to x. The limits will be different, obviously. For example, like if I were to just use either formula to find the length of sine curve, then my limit in the first case would be from like 0 to 1, and then the limit in the second case would be from maybe 0 to pi over 2, where I have the sine graph getting its max value. So we have derived basically two separate formulas to find the arc length of the curve. And now that we have that, let's just do some example problems. So the first problem is we're given that y is equal to 4 root 2 divided by 3 x to the power of 3 over 2 minus 1. And find arc length on the interval 0 to 1. So let's just apply the definition, and let's just, because we're given and also this is x equals 0 to 1. Since we're given the interval for x, we'll just do it by finding dy over dx. We know dy over dx is simply equal to 3 over 2 times 4 root 2 over 3 times x to the power of 1/2. these cancel out, and I'm left with 2 root 2 and 2 root 2x. And so applying the length formula, I get length is equal to the integral from 0 to 1 of the square root of 1 plus dy over dx whole squared, so 2 root 2x all squared, and then dx, which simplifies to 1 plus 4 times 2x, so that becomes 8x dx. Now I can use u substitution over here on this inner side, and I get w is equal to 1 plus 8x. Therefore, dw is equal to 8 dx, and therefore dw over 8 is equal to dx. And so I'm finding the integral of the square root of w from w divided by 8 dw. And then this simplifies to 1 over 8 times 2 over 3 times w to the power of 3 over 2, which then simplifies to 1/12, and then I'll substitute in back x. 1/12 times 1 plus 8x, 1 plus 8x to the power of 3 over 2, and then I'm evaluating that on the interval of 0 to 1. Now, finally, I get 1 over 12 times 9 to the power of 3 over 2 minus 1 to the power of 3 over 2. So the square root of 9 is 3, cubed is 27, so I get 27 minus 1. And then that gives me 26 divided by 12, which simplifies to 13 over 6. So this is an example of finding the arc length. Let's do one more example of finding the length of a smooth curve. This question asks, find length of y is equal to x to the power of 1/3 from the points minus 8, comma minus 2 and 8, comma 2. So if you recall, the derivative of y equals x to the power of 1/3 in terms of, so dy over dx is equal to 1 over 3 times x to the power of 2/3. And if we were to recall that one of the conditions for us to use the arc length formula, at least like the version with dy over dx, is the fact that we need this derivative to be defined in our entire interval. But this derivative is, well, so dy over dx is undefined at the point x is equal to 0, and that's right in between our interval of -8 to 8. So we cannot use the arc length formula that relies on dy over dx. But that does not mean that we are completely out of options. We can use the arc length formula that relies on dx over dy if that is not undefined at any point between -2 and 2. And so let's try that. So we know that since y is equal to x to the power of 1/3, y to the power of 3 is equal to x, and therefore dx over dy is simply equal to 3y squared, which is defined on all y's. And so the arc length will simply be from -2 to 2 of the square root of 1 plus 9y to the power of 4 times dy, and you'd have to use a calculator to find the the concern of the problem right now was just not actually, so concern wasn't finding the exact arc length, it was just coming up with the right integral to find it. So once we evaluate that integral, we would get the arc length of this curve. So sometimes one of the formulas won't work because it's undefined, but that doesn't mean we cannot find the arc length, because if we re-express it in terms of the other derivative, we may be able to find the arc length. And so what if like we have a function that has like an abrupt corner or tangent, vertical, or in that other case we had a vertical tangent. But what if like we have some abrupt corner or a cusp, right? So for example, if you have the curve y is equal to x squared minus 4 absolute value of x minus x on x is equal to negative 4 and x is equal to 4, what happens is, well, one thing we can do with this is we can rewrite this as um, x squared minus 4x minus x. And so this happens when x is greater than um, or equal to 0, and that just simplifies to x squared minus 5x. And when x is less than 0, we get x squared minus 4 or plus 4x plus x. Or actually, no, we don't get that. We get x squared plus 4x because of the absolute value is simply going to convert this into a negative number. And so we need to make that plus 4x, and we still have minus x. And so this will be x squared plus 3x. So indeed, we have a piecewise function. When x is less than 0, our function is, so this is f of x. When x is less than 0, our function is x squared minus 4x minus x. And otherwise, when x is greater than or equal to 0, so this should be if, um, otherwise our function is x squared minus 5x. And if we were to, or uh, so this is x squared plus 3x actually. And then otherwise our function is x squared minus 5x if x is greater than or equal to 0. And if we were to graph these functions, we would get something like this, where we would have the first function and then we would have the second function, and we'd have two parabolas like that. Now, the point over here at x equals 0 is always a function where dy nor dx are defined. But what we can do is we can take two intervals. So if we want to find out the length from negative 4 to 4, let's just first do f prime of x, which is equal to 2x plus 3, and then it's equal to 2x minus 5 on x is greater than 0, x is less than 0. Since we don't have to since our derivative function just has to be continuous on the open interval, what we can do is simply just take the integral from negative 4 to 0, which is our first integral, and that will be of 1 plus the square of this, 2x plus 3 squared dx, and then add that with whatever we get when we take the integral from 0 to 4 of the square root of 1 plus 2x minus 5 squared dx, and that will be our total arc length sum. So that was finding the length of different curves using integrals, and hopefully the derivation made sense as well.